Let's say you have a plane floating in space and a point somewhere above it, and you wanted to find out how far it was from that point to that plane. Well, you could find the distance from the point to the plane there, or to that point on the plane there. But the shortest distance between the point floating in space here and the plane is the distance to the point directly underneath it at a right angle. In other words, where the line comes down, a line comes down and meets that plane, where the line meets the plane at a right angle. Here, this line meets the plane, but not at a right angle. This line right here, this line segment, is going to be the shortest of all the possible line segments where the point out here and the point on the plane create a line. So it's this line segment we want here, the length of this line segment we want here, when we talk about the distance between a point and a plane. I've changed the color of this point to green and the color of this point to yellow, just so that they stand out a little bit more. And we're going to call this point, the green point, x1, y1, z1. That point is fixed, if you will, in space. That's the point that we're interested in finding the shortest distance between this point and the plane. This point, well, we kind of need to know what that point is. So what we're going to do is we're going to take any other arbitrary point. I'm going to go ahead and grab this one, but I could have grabbed another one from here. I could have taken this one. I could have taken a point from anywhere else on the plane. I'm just going to go ahead and take this one because it's already here. And I'm going to call that point x naught, y naught, z naught. Now, when you have 2 points, you can say, well, I have a line. And if I continued this, beyond this point here, and I continue the line beyond this point here, I could call that a line. Equally though, starting from one point and going to the other, I could call that a vector. Let's call this vector v. And then let's also recognize that we have 2 points here and here, one on the plane, one out in space, just as we did here, that I could choose to view as a vector as well. I think I'll use a different color for this. Let's use yellow. This is actually the line segment whose length we will be looking for. So that vector right there. Let's remember that a vector perpendicular or orthogonal to a plane is called normal to the plane. So any vector perpendicular or orthogonal to the plane is called the normal vector, and we usually use n for that. As I said, any vector that is perpendicular to the plane is normal to the plane. So I could, in fact, take this whole little vector here, this whole little setup, and move it to here, and that vector is also normal to this plane because it's at right angles to the plane. So if I choose to call, I'm going to move that out of the way. If I choose to call this vector, vector n, then what I have in this situation where I have this vector v projecting onto the normal vector, I have the projection of v onto n. Now we don't actually need the whole projection because the projection is a vector, right? That would be this vector here, a normal vector with this specific length. What we're looking for is the length of that vector. And that's a real number. So what I want is its absolute value. This could be a negative value, but since I'm looking for a length than a magnitude, then this number has to be positive. So I'm going to take its absolute value. Just by way of reminder, the projection of v onto n has the formula v dotted with n over the absolute value of the vector n's magnitude squared times the vector n. In other words, we're going to take this vector and scale it and multiply it, dot it with the vector that's doing the projecting. Okay, that's the formula for projection, but that gives us a vector. It gives us a vector because we are effectively multiplying, dotting v with n, dividing that by the magnitude of n, and multiplying that by n divided by its magnitude. In other words, we wanted n to be a unit vector, so we took n and divided it by its magnitude. That gives it a value of a length of 1, and we're multiplying it by this, basically this constant, right? This dot product, that's a constant, that's a scalar, and this is a magnitude, so that's a scalar. This part of this formula is the thing we call the comp of v onto n, the component. So let's take this piece of this projection formula and write it over here. The comp, the component, is v, in this case, dotted with n, divided by the magnitude of n. Now, a dot product can be negative. Since I want the absolute value of the component, I also want the absolute value of the dot product. So if the dot product turns out to be negative, this guarantees that it's going to be positive, and it has to be positive in order to be a distance. If it turns out that you have a negative normal vector, then what's happening is that your vector is protruding below the plane. And if what we do in order from this vector to get this one is we just negate it, right? So if you end up with this as your normal vector, taking its absolute value just gives you this vector. So that's how we can get away with just saying, oh, I want it to be positive. Let's take the absolute value. So I now have a formula for, your textbook calls this distance. What they're talking about here is the distance from this point to the plane. This is the shortest distance from the point to the plane. That's what we mean by the distance between a point and a plane. And we have the formula for that now, but what we don't know is what is v and what is n? What are their components? How do we do this computation, this dot product and this magnitude work, if we don't know what the components of these two vectors are? Well, we know what the components of v are because we know how to take the endpoints, the initial point and the terminal point of a vector, and describe it using those values. So v is equal to the terminal point minus the initial point for the first component, and so on. That is my vector v. Let's see, I was going to move it down, but I can't, so I will change this a little bit. The vector v is equal to that vector right there. Okay, so I have vector v, and I can now plug that in up here. So what is vector n? Well, vector n is this vector right here. Well, it could be any of the vectors orthogonal to the plane, but we're going to use this one because it's conveniently located where we want it to be, so that this is right below the point we were given. But how do you find the components of vector v? Let's take a step back for the moment. I'm going to erase this part later on, but just to remind you, the equation of a plane looks like this. A times x minus x, I wrote that down wrong, x minus x naught, plus b times y minus y naught, plus c times z minus z naught equals 0. If I distribute, I get ax minus ax naught plus by minus by naught plus CZ minus CZ naught equals 0. And if I reorder those terms, I get AX plus BY plus CZ minus AX naught minus BY naught minus CZ naught equals 0. And then we're just going to take these values, remembering that A, B, and C are just the numerical components of the vector n, and x naught, y naught, z naught are the numerical components of a point on the plane. A point we could have chosen from anywhere, but we've chosen this one, and its components, numerical components, specific numerical components are x naught, y naught, z naught. They might be 1, 2, 3, or they might be -2, -17, the square root of pi. I have no idea, but they're numbers, right? X, Y, Z is a generic point. X, Y, Z in the equation of a plane. X naught, Y naught, Z naught is this specific point. All right, so since A, B, and C are numbers, and X naught, Y naught, and Z naught are numbers, we can call negative A x naught minus B y naught minus C z naught. Let's give that a name. Let's call it D. So we end up with this, AX plus BY plus CZ plus D equals 0 for the equation of a plane. So that's a quick reminder about what the equation of a plane looks like. But the A, B, and C that we used in this formula come from the vector normal to the plane. So our vector n is just the vector A, B, C. So this is the formula that I'm trying to build out. I now have a vector v, right there, and I now have a vector n. It's right here. Keeping this formula in mind, in fact, I think I'd like to try to move just this part here over. I'm just going to stick it over here, and I'm going to erase the rest. This is the equation for plane. We're going to come back to this in a few minutes, but we don't need how we got there. We don't need this part anymore. Do remember, though, that I'll just move that part over. Negative AX naught minus B y naught minus CZ naught equals D. That's how we came up with the value D here. All right, so let's erase the part we don't need. And I'll move this little bit that's left here, this reminder. I'll move that over here, because we might want to refer to that later. And then we're going to continue building our formula. This is just sort of the first aspect of it. This is where the formula is going to come from, basically. So I have a V and I have an N. Let's go ahead and find that dot product. I have V dotted with N, and that's going to be the first component of the first vector multiplied by the first component of the second vector, the second component of the first vector times the second component of the second vector, and the third component with the third component. Once we have those products, we're going to add them together. So I have x1 minus x naught times A, y1 minus y naught times B, and z1 minus z naught times C. We'll add those products together, and that is a dot product, right? So what I have now is the dot product of V with N. I need to take its absolute value. But I also have another way of writing this. This is equivalent to AX1 minus AX naught plus BY1 minus BY naught plus CZ1 minus CZ naught. You may recall from our work on the equation of a plane that we decided to call negative AX naught minus BY naught minus CZ naught, we decided to call that D. I'm going to rewrite this again. AX1 plus BY1 plus CZ1 minus AX naught minus BY naught minus CZ naught, and then I can write it one more time as AX1 plus BY1 plus CZ1 plus D. Okay, so one way to write the dot product is as the dot product of two vectors. Another way to write it is as the multiplication, the sum of products of components. But then there are other ways to write it, and all I've done here is distribute, redistribute or reorder the terms, and then substitute D for this expression here. The expression negative AX naught minus B naught minus CZ naught. That came from here. Okay, we called that D. Now, so that's my dot product. That's the numerator of this formula, if you will. So I'm going to have, I don't know if I'll be able to squeeze this in here, but let me give it a try. Okay, so I was not able to squeeze it in. And this software is weird because it's weird for a lot of different reasons. One of them, though, is that it will let me move things when I'm not recording, but once I start recording, they go back. So I really have no choice but to sort of move things while I'm recording or just rewrite them, right? So here I've kind of done a combination of both of those. So what I had before was that the distance is the magnitude of this vector, which is just the component portion, the scalar portion of the projection, right? And that can be written as a dot product's magnitude, or the absolute value, the dot product divided by the magnitude of a vector. And this dot product turns out to be just this. Okay, so what's left now is to figure out what the magnitude of this normal vector is. Well, that part, hopefully, you'll find is easy. We should know that formula from pretty early in the course. If I take a squared plus b squared, the components of the normal vector, and c squared, and take the square root of the sum of those things, that is what a magnitude is. So I can write the formula for distance this way or this way, and this is the way we're going to use it. From the formula now, I need to know what x1, y1, and z1 are, but that's the point that's given to me that's floating in space away from the plane. I need to know what a, b, and c are, but those come from the equation of the plane in this form. And D also comes from the equation of the plane in this form. If the equation of the plane is given in a different form, you may have to compute D. But this is our formula. This is the thing that we've been trying to build. This is how you find the distance between a point and a plane, the closest distance between those two objects. Or at this point, I think the best thing to do is do an example. All right, here is our, I need to move a few things around. Here is our question, and I've just recopied or moved our formula to the top right-hand corner here so that we have it to refer to. And here's the question we're being asked to answer. The point 201 is the point floating in space, so that is our x1, y1, z1. Those are our values for those three numbers. Now the plane is given 2x minus y plus z minus 12 equals 0, and that's my ax plus by plus cz plus d. I think I'll use yellow for this. A is 2, b is negative 1, c is positive 1, and d is negative 12. Okay, so I have my a, b, c, d, I have my x1, y1, z1, and I'm ready to go. Let's go ahead and plug those in. In this case, D is equal to the absolute value of A, 2, times x1, 2, plus B, negative 1, times y1, which is 0, plus C, which is 1, times z1, which is negative 1, plus D, which is negative 12. And that is all over the square root of a squared plus b squared plus c squared, didn't give myself enough room, c squared, where a is 2, b is negative 1, and c is positive 1. And the rest is arithmetic. I forgot to close my absolute value bars on the numerator there. 4 minus 0 minus 1 minus 12, the absolute value of that, all over the square root of 4 plus 1 plus 1. 4 minus 13 is negative 9, absolute value, over the square root of 6. So I have 9 over root 6. That's the distance from the point to the plane, the point 2, 0, negative 1, to the plane 2x minus y plus z minus 12 equals 0. That works out to be approximately 3.674. I really like exact values, but sometimes it's handy to put an exact value into a decimal approximation form because how big is this really, right? Here we can say, well, whatever our units are, we know it's a little more than 3.5 of them, right? We can look at that and say, oh, that's how big that is. Whereas looking at it in this form, it's really difficult to tell. I had no idea this was 3 and a bit. So this is my answer to this particular question. I would maybe highlight both of these. That's the distance from the plane 2, 0, negative 1, sorry, from the point 2, 0, negative 1 to the plane 2x minus y plus z minus 12 equals 0. That's all we need to do here. I'm just going to make a really quick side note, and it's almost irrelevant, but I just want you to be aware. If you're bored with this video at this point, you can safely stop watching. The next two little things I'm going to show you are why do we rationalize denominators, and do we really need to do that? And then the other part is, how do you find out how big the square root of 6 is? So they're really irrelevant to this course. They're just kind of interesting information. At least I think they are. If you're not interested, feel free to stop watching, and I'll see you in the next video. A lot of times we're programmed almost to the point of needing to rationalize the denominator. If I do that, I get 9 root 6 over 6, which reduces to 3 root 6 over 2. That's the exact form, but so is this. Now, there's a pedagogical reason for teaching you how to do this, to get from here to here. There's a reason for needing to know how to do that in other courses. So we build it into the curriculum really, really early so that you know how to do it. Also, there's a historical reason for needing this skill. Instead of making a table of values before calculators, before computers, you had to look up approximations for things like this in a big book. And instead of making a table of values that included both numbers with roots in the denominator and roots in the numerator, they only published the ones where the roots were in the numerator. So if you got one where the root was in the denominator, you had to convert it so that you would know which value to look up, basically. We don't need it for that reason anymore, but we still need it for some calculus. So we still teach this skill, but I don't care if you rationalize the denominator. That's not something that is going to make any difference to your ability to do linear algebra, right? So this answer is perfectly acceptable in my book. And this one is valuable from the perspective that it tells me how big this number is, right? I don't know how big 9 over root 6 is. And if I stick it in the calculator and figure what the decimal approximation is, then I get a little bit better idea. I could also say that the square root of 6, let me back that up a little bit. 6 is between the two perfect squares, 4 and 9. So root 6 is going to be between the square roots of those numbers. That was a weird arrow. So I'm going to get 2 is less than root 6 is less than 3. So root 6 is somewhere between 2 and 3. But it's closer, 6 is closer to 4 than it is to 9. So root 6 is closer to 2 than it is to 3. So, but not by much, right? It's 2 off, let's do it this way. 6 is 2 off from 4, and it's 3 off from 9. So it's less than halfway, but not by tons. I'm going to say, just kind of an educated guess, that the square root of 6 is approximately 2.4. I want to say 3.5 even, maybe 2.35. This is just my best guess. Let me stick that in the calculator. I'm just curious. It turns out it's actually closer to 2.45. I wasn't too far off, but you get a sense of about how big that number is using this little trick. I can then take 9 and divide it by 2.45 to get the approximation 3.6-ish, right? This is actually 3.7 if you round it up. This whole little section here from when I circled this onwards is just a side note. Why do we rationalize the denominator was one part. Um, how do you figure out how big the square root of 6 is? That's another, that's kind of a trick that I've used for a long time. None of that's really necessary to this course. I just kind of like to throw stuff that in like that in every once in a while. Plus it's late and I'm tired, so I'm kind of rambling. Um, this is um, this is the video on how to find the distance between a point and a plane. We've done all the theory. We did all the theory on the previous screen. We've done an example, and this is how you find that information. The rest of this, just kind of gravy.